Okay, so this is ICP Unit 2. This is the third video. Excuse me. We are still in Section 2. So we just finished talking about Thomson and his cathode ray tube and his model of the atom known as plum pudding. The next one comes from Ernest Rutherford. Rutherford developed his model of the atom while working with radioactive particles. So Rutherford is conducting experiments and looking for an interaction between radioactive, positively charged alpha particles. This is their name, alpha particles. And how do they react or interact with solid matter? So an alpha particle, this is an alpha, it's the Greek version of A. It looks just a little bit different. So here's an A, and this is an alpha. An alpha particle is positively charged. It has, we'll talk more about protons and neutrons and things later, but it is basically a helium atom that's just a little bit different. So this experiment that we're about to talk about is now known as Rutherford's gold foil experiment. In this experiment, a narrow beam of alpha particles is aimed at a thin sheet of gold foil, that's where it gets its name, to observe the interaction. So here's what we're looking at. This is the basic setup. So over here we have some sort of a container, and inside of it there is a radioactive substance. I'm trying to make that the radioactive symbol. Okay, well, so here it is. And there is a small opening right here, which is going to allow these alpha particles to shoot out. Since there's only one small opening, they can only make it out this way, and so they're going to come out in a nice straight line. Over here we have some sort of a detector. So it's going in through this opening, and everywhere along the circle can detect when one of these hits it. So detector. Okay, so we labeled it here. Radioactive substance, here's the detector, here's the alpha particles in a beam. And the last piece of this experiment goes right here. And this is the gold foil. Let me change colors so it stands out a little better. This is, here we go, the gold foil. This is really thin stuff. So you're familiar with aluminum foil, and it's very thin, but it's still pretty strong. Gold foil would be 100 or 1,000 times thinner than your aluminum foil. So we're talking about a very thin sheet. So what happens is these alpha particles are flying in, and we're going to see how do they react with the gold foil. The reason that we use gold is because we want to see how do these things interact just based on their structure. And gold tends to not have chemical reactions. That's why it lasts so long. That's why it always looks shiny thousands of years after you dig it out of the ground. We want something that's not going to have a chemical reaction with the alpha particles. So 2 possibilities for the results. So I'm going to draw 2 different scenarios here. Here's the box with the radioactive substance. Here are the alpha particles coming out. Here's the detector. So what's going to happen is, let's say that we have the Thomson model of the atom. And let's say that's what actually works. They're solid spheres with a positive charge, and they have those electrons just stuck on the outside. And so the thought would be that somehow these alpha particles just have so much energy that they're all going to go right through these atoms. Every single one of them. They're not going to touch, they're not going to do anything, they're just going to go straight through, like you could walk through a wall. Which means that every single one of them would be hitting right here on the detector in a straight line from where they came out. The other possibility here's the alpha particles. Here's the detector. Try that again. Here's the detector. Here's the gold foil. This is what actually happened. Most of them were going through just like they expected. But then they had some things they weren't expecting. Some of them were shooting off in this direction. Some of them were shooting off in this direction. Some of them were kind of bending off, and they're all going in different places. So you might have one that hits here. You might have one that hits here. One that hits over here. While most of them are hitting where they expected, but they're getting random hits just everywhere, all over the place. So it's not what they expected, so they have to go back and look at their results. So here's what they're thinking. So most of the particles pass through. But some are deflected. Basically means they bounce or something. Somehow they are being put off course. They're no longer going in a straight line. They are going off at different angles. Here's what they decide. So this gold foil, maybe actually everything is really far apart. And so we're getting these alpha particles that are coming through and just going by. Some of them may be getting close, and they're being changed in direction just by being close to them. It's kind of like if you have 2 magnets and you put the same ends together and they want to bounce apart. So the alpha particles coming in, they don't want to touch, it's going to go that way. Here's one coming in, it doesn't want to touch, it's going to turn. That's the idea behind it. And this is actually the thing that we see happen. Most alpha particles pass through. Thomson model didn't really work like they expected it to. So if the plum pudding model had been correct, every particle would pass straight through. This was their thinking. Rutherford found that most of the alpha particles were able to pass through. They are passing through the gold foil, and this gave him the idea that the atoms are probably mostly empty space. But some of the alpha particles were deflected, meaning that something was hit by the alpha particle. His experiment leads to two discoveries. So the first one, atoms are mostly empty space. You'll definitely want to remember these two takeaways. So atoms are mostly empty space, and number two, almost all of the mass of an atom is in a tiny dense region at the middle of the atom that he called the nucleus. So the gold foil experiment is going on around the time of 1911. He comes up with this sort of an idea. So here is a positively charged nucleus. This is our tiny dense region in the center. And negatively charged electrons are just floating around outside the nucleus. The problem you might think about is if you ever hold the opposite ends of a magnet together, so the north and the south pole of a magnet, just like here we have the negative and the positive end. If you put them close together, if they're close enough to be held in, then they're close enough to keep coming together, and eventually your two magnets are going to click together. The same thing here, opposites attract. These electrons are probably going to be pulled in and eventually hit, and then we have a problem. This model of the atom has changed. I've got a note here. Rutherford discovers protons in 1917. So about 6 years after the gold foil experiment time frame, he's doing other experiments. He discovers protons. The next model of the atom is developed by Niels Bohr, and the official name is the Bohr model of the atom. Sometimes it's referred to as the planetary model because it has a resemblance to the solar system. If you think about an atom, this is probably the model that you're picturing in your head right now. The electrons are orbiting the nucleus, at the center of the model is the positively charged nucleus. The electrons are orbiting it like the planets orbit the sun. Bohr's model of the atom answers some important questions. Maybe we'll talk about them later. It's helpful because when we draw atoms in this course, we will use the Bohr model because it's relatively simple and it's easy to draw. So here is an example. So let's say here's the positively charged nucleus, and let me draw, here's an orbit, here's an orbit, there's an electron, there's an electron, here's an electron, here's an electron. It's the sort of thing we're looking at.